Well, thank you. I get that buzz every time I turn this on. So there.
We need to reset this if we're going to do it.
Hey, folks, thanks for coming out on a cold December night. It's an honor for you to join you. Let me say hello from Indiana. That's where I live. Although my family and I, we like to come out here hiking in Colorado. You've got more hikes than we have back there in the flatlands. So I don't know whether to turn this on or not because it always gives that big feedback thing. Hey, let me start telling you just a little bit about the Creation Research Society. That's not our whole talk, but just to kind of say something. Hello? Sounds like kind of hollow, but at least it's not buzzing at us. Good work there. So some of you belong to this group. It's been around for a while, so I'm just going to again say just a little bit about it. Got some pictures to go along with it as well. In fact, I started a list of all these interesting groups. You know, they're all related. They're all doing good work in this modern creation movement. So these are all the ones you've heard of, all these initials going on, and I kind of have their dates of when they started as well. I'm not sure when the Rocky Mountain group started. You might be the oldest of all, but I put you at the bottom of the list here. So there it is. But what I wanted to say is that the CRS is kind of the granddaddy. All these other groups have split off from it. So that's one thing I like about the Creation Research Society. So let me say a little bit more about that top one, formed 54 years ago, way back in '63. And some of the early board members before my time on the CRS, DeYoung Gish, George Howe, Henry Morris, these pioneers that kind of got the whole thing started. Our board members today include people like Gene Leitner and Russ Humphreys, Mike Ord, and about 12 other people as well. In fact, the CRS, we currently have
if you don't want to fade it, all you have to do is hit the play button and it'll switch.
We have Tim Clary on our board, and representatives from CMI, Rob Carter, and from AIG, Danny Faulkner. The CRS, we try to stay friendly with everybody and help all these different groups, and that's a real effort that we work on. We're a volunteer, unpaid board. We serve 3-year terms, and it's a lot of fun that we do. We meet at least once a year for a whole weekend where we plan a budget and do all that kind of thing. We'll be in Prescott in June. We've met in Denver before, our board of 15 guys and gals, and I'm thinking it's time to come back again one of these Junes and meet up with you guys and encourage each other, so we'll see what we can do there. The CRS just has 2 full-time employees. You may know them, Kevin Anderson, who directs our lab in Arizona, and his wife Diane, who's a secretary. That's over in Chino Valley, Arizona. So the CRS has about 1,600 members, including many of you. And it's kind of a unique group in that it's a membership. We have a lot of professional scientists, guys and gals, but anybody can join our CRS as well. We have funds. We have modest endowment funds, and we fund research. People make applications for whether they're working on desert plants or planets or whatever. 2 current projects that we have going are named iKinds and iDino. In fact, the iKinds project is to kind of research the meaning of the biblical word kind, as you see in Scripture and in nature. Gene Leitner's carrying that one out. And that other project, iDino, that includes the analysis of tissue that we're finding in dinosaur bones, and Kevin Anderson is working on that. So that's what the CRS does. We try to conduct research. Really, we purposely kind of keep a low profile. We just want to do stuff and then pass it on to others. And also the idea is to encourage local creation groups like the Rocky Mountain Fellowship as well. So maybe that's enough commercial, but that's the CRS. It's a good group and kind of working together with you folks. So anyway, for our time tonight for a little while, we're going to talk about mathematics. We had one more Creation Research Society shot there. That's some of the things we do. We have a quarterly with technical articles, and Creation Matters, which is a more readable magazine, newsletter, books. If you don't belong to this group, you should. The price is good. You get this kind of literature and kind of keep up with things, so there. Let me go on with our talk here, because time's rolling along. I don't know, mathematics. Does this sound like a positive talk? We'll keep it that way. And a dog is even going to show up as part of this talk, so we'll see what we can do with that area as well. I don't want to go heavy or deep on a Friday night, but just appreciate creation and how this all goes together. You know, mathematics is the language of creation. God's embedded it lots of ways. So that's what we're going to take a look at for a bit. I thought for a little outline, I would kind of break this up into parts. So we're going to have a calculation. We're going to do something, figure something out. And then we'll have an example of mathematical design in nature. And then we'll talk about a mathematician, a person, a guy or gal, who had a godly view. And then something called anticipation, where math kind of gets ahead of nature in explaining. So I'm going to go through that. And then I'm going to go through it again, kind of like a cycle. So we'll hit a calculation maybe 3 times. We'll go through this. Anyway, I was kind of thinking of a way to just kind of keep ourselves occupied. So that's the plan. So if you're keeping track of it, that's our outline. So we're going to start here with our first calculation when it comes to this stuff. And let's go right to an interesting problem. Are there aliens? You know, we all kind of look at this stuff, and the kids are all into it. So, by the way, do you see who I put in the flying saucer? That's the VeggieTales. The grandkids know all about those guys. So, how about this question here? What should we think about this with our whole creation biblical worldview? Now, there's an assumption. And you see this when you read newspaper articles about the latest space probes and they're looking at nearby planets. I've noticed this. There's an assumption that if we can find some new planet, and maybe it has some liquid water on it, and then maybe an energy source like a star or sunshine, and then if you let enough time go by, life will show up. Those articles always end up saying we're searching for life. They are finding new planets. They got over 3,000 new planets they have found. Not going around the sun, but going around other stars. So that's a very active area of research. So anyway, this is some of a sort of a grand assumption here, this formula, and I want to say I don't think so. It's not this simple. To get life, you don't just add water. As you know from the study of a cell, complexity beyond what we can imagine, and it goes on and on. So so much for that recipe. Anyway, to answer this question of aliens, all I can say is after 60 years of this whole space age, there's not a shred of evidence of life anywhere else. If there was, it would be making headlines. It looks more and more like we're unique, that we're alone. In fact, you know what astronomers are saying? Where is everybody? It might be valves that pops out, you know, we should be surrounded by them now. Anyway, since they haven't found any life, people have gotten quite imaginative. So here's this fellow, Frank Drake. Now, he's 87 years old, but he's still around. And he has spent his whole life thinking about aliens. That's been his push in life. He was a professor, now he's retired. And so what he has done is he's come up with a formula to calculate how many aliens there are. So this is our first calculation. I kind of want to show you what he did. No quiz, you don't need to take notes unless you want to. But here's the gentleman, and there's his formula. Now, let me kind of enlighten that a little bit. Here's what he says. Let's calculate the number of planets in our own galaxy and our own Milky Way that have life on them. That's what he's searching for. So here's his formula that he makes up. Little n, the number of stars in the Milky Way. It's a huge number. That's our galaxy. That F stands for fraction. So now we have the fraction of those stars that have planets. Because you can't live on a star. You have to live on a planet that's circling a star. Then the next fraction is the fraction of those planets that have an Earth-like situation. They got to be solid so something could stand on them, and maybe having some air and water and things like that. And the last fraction is the number where life has evolved. Now, he's tweaked this equation somewhat, but this is one of his versions of it. So there it is. You put in the numbers, and you can calculate big N, the number of planets with life on them. Quite imaginative, isn't he, what he's done? Let me show you the numbers that he's come up with here. The number of stars in the Milky Way, it's somewhere around 100 billion. I mean, it's rounded off, it's an estimate, but, you know, the sun is one of them, but there's lots of stars. So the fraction of those stars that have planets, maybe 10%. So you put in a 0.1. See how that kind of cuts it down a little bit? How about the number of those planets that are Earth-like, where they have a solid surface? Maybe 10% of those. You put in another 0.1. And then you get kind of optimistic and you put in a whole 1 for that last fraction. And you come up with the idea that there must be in our own Milky Way 1 billion planets with life on them. Wow, that's quite impressive. He writes whole books on this kind of thing. Frank Drake. Now, already I've shown you something that has something questionable on it. Now, I don't know if you were with me, but would you challenge anything on this screen right now? Anything look a little suspicious? What would you say?
The last subscript.
Oh, the last number.
The last number.
You caught it. It's very optimistic. What these people usually assume is that if you've got planets, if they're Earth-like, life will show up. So they put a probability of 1. And that's where he gets his big number. Again, it's that last number that is the questionable one. So even though that's what Drake's book kind of comes up with, let me change that a little bit, because that last number, it's 0. Life does not evolve on its own. All the probability arguments show that it can't happen. And so if you put a 0 in the last term, the rest of them don't even matter. There is no evolved life in the galaxy, and they haven't found any either. Now, I want to be careful, you know. God could have put life somewhere else. I don't know why he would, but we haven't found any such thing. So that's where those formulas go. You can't even calculate life in space. It comes out to be 0. So we need to move on and talk about other things. But my conclusion on that whole idea of life in space, there was that question again. I think there is some scripture that kind of hints at the idea of aliens. So here's a verse in Psalms 115. The highest heavens belong to the Lord, but the earth he's given to man. The heavens don't belong to aliens. They belong to God. Now maybe, I'm sure there's a spirit world, there's angels, but crazy alien types, it's not going to go. So anyway, that was our first calculation. It kind of came up 0 for evolved life. So the next thing we had on our little outline was just to look at some ideas of design and nature. And so here are just some pictures of these interesting spirals. Just got some ammonite shells here. Those all seem to be fossils. Is that an interesting shape? And now, as you know, there's mathematics behind all this kind of thing. And if you're taking notes, here's one way you can write an equation for these spirals, and you can graph this and do computer work. There's integrals and trig functions and all that. Very interesting. Anyway, we're kind of surrounded by that mathematics and by spirals. Here's a couple more. On the left, that looks like a tendril of a vine that grows. That could be a number of things. Anyone know what that deal on the right? I mean, besides the dime, what is that? Those little guys there. Those are seeds. Those are self-planting seeds. They grow down in Arizona. They're called filary or filaria, and it's like a weed. And they blow across and they hit the sand. The heavy part hits the sand and sticks in. And then as the moisture and humidity changes, those things spin around and drill themselves down into the ground. A self-planting seed. What will God think up next? There's nobody out there in the desert, so these things just take care of themselves. It's an amazing plant. I have some of those seeds, and I tried to grow them, and they promptly died. They do fine out there in the desert by themselves, but I could not propagate them myself. Well, still going along with this idea of spirals, now here's a inventor. Actually, he's down in Australia, and Jay Harmon, and he comes up with new ideas. And he got to looking at the spiral shape and realizing that it's very useful. And so there's some other kinds of pictures here. Let me tell you what this guy has done. That's his company, Pax Technologies. He was looking at this calla lily. That's the picture on the left. And he kind of modeled the shape of that lily with this metal spiral. And he found out that that kind of spiral is just very efficient at stirring up water, more than just a fan blade or something like that. So they're starting to take this kind of spiral, and they'll put those, let's say, in a water tower. You got to keep that water moving. It just keeps it healthier. And they're finding out that a very small impeller like this keeps thousands of gallons of water moving, somehow using the spiral that's in nature to help this whole idea of fluid dynamics. It's really neat stuff how that works. And now they're thinking they can build these impellers larger and stir up the fog to get rid of it at an airport. and all sorts of ideas that go on and on. By the way, as we're going through this sharing time tonight, I believe that the Creator has filled up this world with endless ideas for new inventions, solutions to problems, including things like this impeller. It's a whole new way to look at science, seeing the secrets that God put there for us to use and make use of. This has made science kind of interesting for me, just looking at God's fingerprint, the way He's made things, and then we find them one by one. In fact, a student and I, back in Indiana, wrote a book, Discovery of Design, where we collected 100 of these ideas. You've heard of some of these design ideas before, like Velcro, which was discovered from cockleburrs or from feathers with the little hooks that they have. And we've started this website where we're collecting hundreds of more of these ideas. It's called Biomimicry. It's the idea of design in nature. It's just a great application of science studies. So anyway, the commercials go on. First I was talking about the CRS. Now I have this book. We got to go on ourselves. Although let me show you one other design that's more recent, things that they're finding in nature. Okay, so here's another extra design idea. It involves spiders. You say, well, I don't like them. Spiders, well, you know, all these things teach us, and we have things to learn. So there's something about spiders that is very curious that we've come across. Now, before I get back to the spider, let me mention another creature, birds. Oh, there's one in the wintertime in the lower picture there. Have you heard before a bird when it flies into a window? I don't like that sound. You know, they hit, and then they're on the ground kind of shaking their head. Sometimes they make it, sometimes they don't. You know, they see a window and they think it's either an opening, or maybe they see a reflection and think it's, you know, and so they hit the window, and that's not a good thing. So, back to these spiders. Birds do not fly into spider webs. They avoid them, even at night. What we have found out is that many of these spiders, they take their web and they coat it with a film of material that reflects ultraviolet light. Now, we can't see UV, but birds can, many birds. And so birds can see this web, even in the darkness, and avoid it so they don't hit it. Of course, the spider doesn't want them to do that. They would tear up the web and mess up the bird. And so spiders, pretty smart little critters, equipping their web to avoid birds. So people have looked at this and thought, maybe we can make use of this. So what's being done in these large buildings with the big windows? They are coating the windows with invisible strands of the same kind of material that reflects ultraviolet light. Now, you can't see it, so if we look at this window, it'd be like the one on the left. But when a bird sees the window, he sees like a spider web, so he does not hit the window. Spiders are teaching us how to protect birds. It's design in nature, and the ideas are endless, and it's kind of neat stuff. So I know we're talking about mathematics, and I'm kind of wandering around here a little bit, but we also wanted to mention a few mathematicians. So how about this guy here, Leonhard Euler? Big name in the math world, lived 3 centuries ago. He has a Swiss background. He wrote 70 books, even though he was blind in his later years. And no computer. How did they do this? These are amazing people. He came up with this idea called the Euler identity. That's the little equation down there. In fact, it's on that stamp as well in another form. It's an interesting formula because it has many parts of math in it. It's got the constant pi. It's got the letter E, the base of the natural logarithms. It's a famous equation in the math world. In fact, I kind of like one quote that this guy Euler came up with. For the sake of brevity, we'll always represent this long number by the letter E. Thank you, Euler, for doing that. Anyway, that's, again, a fundamental constant in nature. So Euler and his wife, Catherine, had 13 children. His biography says he was a family man and his faith were his greatest joy. In other words, this man was a godly man. He'd be the kind of guy who'd give a talk to your Rocky Mountain group if he was still around. A man of God. He realized that math was the language of creation. So many of these science guys and gals from the past in mathematics, they knew their creator, and it's like he honored them with great insights as a result of that. So we had a little bit of calculation, a design, a mathematician, this thing called an anticipation. What I mean by this, over and over again, people that are in the math world will come up with some new function or some new equation, and it doesn't seem to be good for anything. And then later on, they'll find that it fits exactly something in nature. This gets repeated. So here's an example of this. Complicated figure there showing an ellipse. Remember what an ellipse looks like? It's like a circle with two centers, and you can kind of sketch those. Well, the math of an ellipse was done long ago by the Greeks, 2,000 years ago, and there it sat. Big deal. It's just sort of a math figure. So along comes Kepler 1,500 years later and realized that that's exactly the shape of an orbit of a planet going around the sun. And used this math that had just been sitting there accumulating dust, and suddenly it's very useful. Again, this happens where you find the math, and then later on you realize that it's useful and it was in nature all the time. Again, the idea of the language of nature. Here's another quick one when it comes to anticipations. You can't see a shirt like this before. Maxwell's equations. Those are complicated differential equations. We don't need to get into that tonight. But anyway, Maxwell came up with these formulas, Clerk Maxwell, along about 1860s. That's my number in the middle of the page. And then about 20 years later, it was realized that those are just the equations we need to explain radio waves. They got them ahead of time, and there they were. It just shows, the intelligence of math, that it's all useful, even if we don't find the application at the time. Since I mentioned the names there, let me just grab a couple quick pictures. There's Michael Faraday, and there's Maxwell. Their lives kind of overlapped. They knew each other, living over in England. Two pioneers here of physical science and mathematics. Wonderful people. They're neat examples to us. Michael Faraday, a very poor family. He was homeschooled. He never learned a lot of math, but he became the greatest inventor of all time. He came up with the first motor, generator, made the first batteries. His bedroom must have been filled with wires and things like that, and made great insights. And there's Maxwell, who had all the math and put those fancy equations together. It's like God raised up these two people. Maxwell would do the theory, Faraday would put them together, and today we're surrounded by motors and generators and everything else that these people came up with. Yeah, their lives overlapped. Well, we just went through a quick cycle here, and we're going to start over again with another calculation. So I thought in December we ought to just bring up snowflakes for a minute here. This morning I was talking at this Christian school. I love these kids. They're a great audience. And I put this picture on the screen and I said, kids, snowflakes, do they have 6 points or 8 points? So let me ask you, because we voted on it this morning, what it should be. And it's one or the other. You know which one it is? It has to do with the way, the water molecules are going to bond together. Now, those are both pretty interesting drawings there. Which one's it going to be? We're not going to vote on it. I'm just going to show you the answer, because you can take photographs of snowflakes and see that they do have 6 points. Now, unless they're partly melted or broken, that can happen. But there they are, that neat symmetry that they have. The kids voted for 8 points, by the way, because they were all looking at each other, kind of peer pressure. So thinking about snowflakes a little bit, here are some more. They take these interesting polarizing pictures of them, and we had a few coming down last night in Indiana and here in Colorado. So the calculation thought here is it true that every snowflake is different? You've heard that before? And someone says, who made that up? The whole driveway gets full of snowflakes. And last year and the year before, how could that be? In fact, sometimes I see two on my sleeve and they look alike. How can they all be different over all of time? Well, I would suggest to you that they are all different. Everyone that has ever fallen. Can I prove it to you? We're doing a calculation here. Let me try this. So instead of beginning with snowflakes, let me begin with a baseball team. Okay, here I've got 9 people. I know they look alike here, but I got 9 figures here lined up. Now, suppose 9 of us would stand up in front here in a row, and we were going to take a picture. How many different ways could 9 people stand? You know, we got 9 slots here, and you could change places. So the first person would have 9 different places where he could stand. Then the next person would only have 8 places. You know, we're taking a group picture. How many different ways could 9 people line up? It's a pretty good number if you think about it. Maybe you've done this if you've taken a family picture. The way you would calculate how many ways 9 people could line up, you've got to take the number 9 times 8 times 7 all the way down to 1. In fact, it's called a factorial, 9 factorial. And if you've got 9 people, there are 362,000 different ways they could line up. You'd wear out before you had every possibility. These numbers are quite amazing, but that's what you would have if you would start to play that game. You know, from tallest to shortest and age and all that, it goes on and on. Now let me apply this to a snowflake, which has more than 9 variables. A snowflake, it does have 6 points. Sometimes a point can have a defect in it. Inside a snowflake are trillions of water molecules. And there are always going to be some impurities in there, an atom of carbon, an atom of calcium. There could be a crystal defect. Inside a snowflake would be like a whole football stadium. And if 2 people change places, that's a different arrangement inside. I would suggest that inside a snowflake there are at least 100 different variables that could happen. The number of arms in the flake, the number of points, impurities inside. So to figure out how many different snowflakes are possible, you would have to take the number 100 times 99 times 88 all the way down to 1. 100 factorial. That's how many possibilities, even conservatively, you could have for snowflakes. And if you do that, you end up with a number something like this. 10 to the 157th power, which is more than all the snowflakes that have fallen since creation, I'm sure. It's a huge number. In other words, yes, snowflakes may look the same on the outside, but inside, there's no way that they would be identical. So there, on the microscopic level. And really, when you think about it, wouldn't every blade of grass be different? And every kernel of corn? And every grain of sand? Certainly every person is different. That's what creation is like. It's just infinite in its variety. So I don't know if I convinced you, but all the snowflakes certainly are unique. But I'm moving on because we got some things to do tonight. So now we're moving back to design again. Last time we had spirals. This time we have Fibonacci. Don't know if you know that name. This guy lived several centuries ago. He was a mathematician, and he came up with what are called Fibonacci numbers. And so here he is. They wore funny hats back in those days, but there he was. And he came up with these numbers. So we have kind of a sequence there. Do you know what the next number will be? There's probably more than one choice, but I've got one in mind. You got it?
8.
You say, I don't need these problems on a Friday night. You got it, was an 8. Okay, then what's the next number? There's always another number with this stuff.
13.
Now, you know what we're doing. You're taking the 2 previous numbers and adding them together to get the next higher number. 3 plus 5 is 8. 5 plus 8 is 13. And it just keeps on going. I mean, it does go. You can get the number 144 in there after a while. Well, this guy Fibonacci, he also liked the out-of-doors. And he noticed that there's something special about these numbers, that they show up in nature with unusual frequency. Here, let me show you what I mean. On the left here, we have a 3-leaf clover. Somebody's pulled it right out of the ground. Now, remember going outside in the summer and looking for a 4-leaf clover? You can find them, you know, good luck and all that. But a 4-leaf clover, that's a mistake. That's a mutation. Clovers come with 3 petals. 3 is a Fibonacci number. Over on the right-hand side is, I think it's a sand dollar with 5 points on the back of it. So this also affects the animal world. This is where it gets even more interesting. if you could find a sunflower and count the number of spirals as you go around the circle with the seeds. Now, it would almost take a pen. You'd have to kind of mark them, but you can kind of see that spiral nature there. It depends on the size of the sunflower, but every sunflower that you'll find will either have the number 21, 34, 55, or 88, 89 in it. It's always a Fibonacci number. Now, there are some exceptions to these numbers, but they show up with unusual frequency in nature. You'll find a lot of flowers that have 8 petals or 13. You won't find that many that have 9 or 10 petals. Again, the Fibonacci's show up. Well, the biology world has never known quite what to do with this, why these numbers seem to show up. You know what I think we're looking at? God's fingerprint. Maybe we don't like math, but he does. And he's put it even, see, that's a complicated formula when you add numbers together to get the next higher one. So anyway, when spring comes, I would challenge you when you go outside, look for these Fibonacci numbers. They're all around us, designed in nature. It's kind of fun stuff. So that's Fibonacci. By the way, one of my friends at Grace who graduated and went into the finance world, he really got enamored with these Fibonacci numbers, and he wrote a book on it. And he's using these Fibonacci numbers to predict the stock market. His book is titled Fibonacci for the Active Trader, and he's having some success. And what he says is that somehow these numbers are part of our makeup, and they even affect our buying and selling. And I don't know exactly what he does with those numbers and the ratios, but he's making a buck off this stuff with a stockbroker's book. So Fibonacci numbers are kind of a mystery, but it goes on and on. Okay, well, we're back to another person again as we're kind of walking through as well. Before we had Euler, so this time we got a gal, Maria Agnesi, her name is. Have you ever heard of her before? Let me find her little right up here. This gal lived in the past as well, and an interesting representative of the math world. Well, I had something on her somewhere. Let me see where this went. She was a wonder. By the age of 10, she had learned several languages. Where's she hiding? Here she is. The oldest of 21 children. They had quite the families back then. Living in Italy. By age 10, she had mastered French, Latin, German, Spanish, and Hebrew. She learned mathematics from her father. And her early years, she overlapped Isaac Newton. I don't know if she knew him, but as they traveled around Europe. This gal had a strong Catholic faith, and she ministered to the sick and the poor, as well as all of the abilities that she had. She became known as the Angel of Consolation. She was a nurse to people that were hurting. In fact, she was later buried alongside those that she had cared for. In other words, she, also a mathematician, had an outstanding life of Christian service to others. She expanded calculus, and she wrote a book on calculus way back in her day, back when women were not really appreciated in the science and math world. She was ahead of her time and ahead of the guys as well. And here's the book that she wrote. That's the kind of the drawing on the left-hand side. She also came up with some new functions and some new graphs over there on the right-hand side. That one is named after her. Anyway, I was noticing when she copyrighted that book. Do you remember your Roman numerals? Just to keep us awake tonight, can you remember, can you come up with what year that is? Boy, it's been a long time since you looked at those. You know, do they still have Roman numerals? Somewhere.
1768.
So you're working on that number there.
1,000.
You got it?
What's a D?
M is 1,000, D is 500. You remember how that?
It is
This goes back to the
1768.
6th grade, doesn't it? 1748.
40.
Yep, some of you nailed it, you hit it, you get credit for that one. So that's when she came out with this wonderful book. And you know, this is parts of calculus that we are still teaching and making use of today. Okay, so we've had some mathematicians, and now we're back to another one of those anticipations where the math came before the application. So there's the first two already had, the ellipses and Maxwell equations. What about matrices? Now those are arrays of numbers. It's just an interesting way to put values together, and then you can manipulate those and do all kinds of things. Matrices were first thought up back in the 1850s, 150 years ago, give or take. And then they've been found to be very useful just in the last 50 years for aircraft design. You can't get along without matrices. So they were thought to be useless for a long time, and suddenly it's exactly what we need. Now, I don't know who this gal Olga Todd is. Apparently she has kind of pushed ahead the idea of matrix theory. I did not look for it. It found me. These people, these mathematicians, they just seem to be gifted, you know, by God to make discoveries, whether they acknowledge the Creator or not. And so she did work in that whole area. So interesting where this math comes along and helps solve these types of problems. Here's another example of one of these anticipations. Have you heard of George Boole, who long ago came up with the idea of binary numbers, 0 and 1? And that was thought to be interesting, but not worth very much, and there it sat until our lifetimes when digital electronics has come along. And binary math is exactly what we need because solid-state switches are on or off, 0 or 1. So all of a sudden this is just what we need, and it was just there waiting for us. There's an interesting article about this whole aspect of mathematics by Eugene Wigner, and here's what he titled it: The Unreasonable Effectiveness of Math in the Natural Sciences. Why do we keep getting these functions that are, you know, graduate students in math come up with, and it's thought to have no value, and later on it's exactly what we need? It's God's print there, and sooner or later we kind of catch up with it and realize just how valuable it is. That's a great article to read, and it is quite readable as well. Are we hanging in there with our math? Because it's time for another calculation. We did the aliens, we did snowflakes, so here's the next one. We have a picture of a shoreline here. And there's some sand. We've all walked in the sand before, somewhere in the Great Lakes or the seashore or whatever. Always kind of fun. So I was thinking about this. Can we, with our calculation, come up with an estimate for how many sand grains there are? Isn't that what you were wondering on a Friday night in December? You know? So we need to do this. Let me go over here to do this because we have a little chart to kind of help us. So engineering type people, and there's a lot of us here, are pretty good at estimating numbers. So first of all, let's say you get a handful of sand. Okay, so you can hold that. Of course, that's got lots of sand grains. I don't think I want to count them all. So let's estimate it. Suppose I have sand like, I want to make this big enough so you can see it, like 1 inch on each side, a cube of sand. So you could hold that. Okay? Now, maybe you could do a little bit of counting. How about, could you count the number of sand grains along one edge here? I guess that's going to depend on the sand grains. We do this in my classes back at Grace College. I make them work. We haul out a ruler, we dump sand on the desk, and we kind of push it around and count them. We can come up with numbers like maybe, this is going to be 1 inch on each side. So it's going to be, you know, 1 cubic inch. And we can typically count like 100 grains along the edge there. Push them up against the ruler and count them, and that's all you want to count. So there's 100 along that edge and along the other 2 edges. So then you can multiply those and find out roughly how many grains there are in the whole cube. 100 times 100 times 100. You can estimate how much sand in your hand. See, what's that going to be? 103 times. You'll have 6 zeros. You'll have 1 million. Okay, let me just write that. 10 to the 6th grains. Okay, so you're with me so far. You say, how do you know that? It's an estimate, but it's probably pretty close. Okay, now let's go there. Let's go to the seashore. Let me estimate that. Here, let me draw this picture. Let's see. I'm drawing a picture of the seashore. Okay. I'm taking the seashore and kind of thinking of it in terms of this big rectangle. And I'm going to make some guesses here. So I don't know how deep the sand is on a seashore. Some don't have any sand, it's rock. Other ones have quite a bit of sand. I'm going to say maybe this sand averages 10 feet deep before you would hit clay, gravel, whatever. Okay, now this here, this is going to be like how big the beach is, from where you park to where you get the water. How wide is the shoreline? Some don't have any shoreline, it's like a cliff. Other ones have more. I'll be generous here. Let me give this 100 feet. Okay, that'd be a pretty good sized beach there. You could, lay out there and get some sun. Okay, these are all estimates. Now, here's going to be the hard one. What is the length of the seashore? In fact, I'm thinking of all the seashores of the whole world. Going around the Pacific Ocean, going around the Great Lakes, whatever lake you have around here. I'm going to add them all up. And I'm going to put down the number 1 million miles. 6 zeros. I'm really guessing now. But a million miles, that would be 40 times around the world's circumference. All the way around the world 40 times. That's maybe a pretty fair guess at the length of all the shorelines. I don't know how else you would find out. I just make up numbers. Okay, can we finish this off? You say yes, please go on. Okay, let me see what happens here. I know that 1 cubic inch has 1 million sand grains. So let me put that down here. This is grains per cubic inch.
You're hitting the remote. You're hitting the remote.
What's going on here?
It was a remote possibility.
Okay, we're back to snowflakes again. Oh, I've lost the whole thing here.
We just went fast a few times.
This is good. This is good stuff.
We agree.
I don't know how I get rid of the boundary stuff. I messed it up. Can you come to my rescue? And then maybe you better hold this. Anyway, while he's doing that, let me finish this off here. Now, here we need to do a little bit of multiplying. What do we have here? 10 feet, and there's 12 inches in a foot. So that takes care of one of the inches. By the way, is anyone going to have a calculator? You're going to have to multiply this stuff I'm doing here. We had 100 feet this way. So let me put in 100, and each one of those is a foot, so I have to have 12 inches. What I'm now figuring out is how many grains of sand there are all together, because this is 1 cubic inch, and this is going to be the number of all the cubic inches. What's that last number? 1 million. So I'm kind of out of room there. I'll just do this on the next line here. We got 1 million. I'll make that 10 to the 6th, but that's miles. I got to change that into inches. Let's see, there's 5,280 feet in a mile, and there's 12 inches in a foot.
No, it's land.
I knew I should have done this on Friday. But I'm done with it there. So we need to take these numbers and multiply them, and this will be our group estimate for the sand grains on all the seashores of the planet. You know what you get if you do this? Because I know what the answer is. It's real close to 10 to the 22 power grains. Try it out, check me out. That's what you'll come up with, I think. So, what was I doing here with the sand grains? Let me get back where I left off here. Yes, because there's something special about that number. Because that's also the number of stars that there are. Amazing how this comes out. What a coincidence. I knew the slide was hidden here. Now, this also is an estimate. We can't count the stars. We count the number in a small little window, and then we extrapolate over the sky and the southern hemisphere. And this is a ballpark estimate on the number of known stars up through this year, 10 to the 22 power. And it comes out same. Of course, I kind of tweaked that estimate there, but it's interesting that they come out similar. As many stars as grains of sand on the seashore. that reminds us of something. Yeah, something about God talking to Abraham back in the book of Genesis, and says, Abraham, your offspring will be as the stars or the sand grains. Not that there's got to be that many, it just means you can't count them. And we are sons of Abraham if we're in the kingdom, and it's just interesting how it does come out that way. So anyway, that was our little calculation exercise. I'm glad we got through that. By the way, I think that there are far more stars than this. Every year, new telescopes show up, further and further. We don't see any edge to the universe. Could it be that there are far more stars than anybody has imagined? Not billions, but trillions and trillions, maybe an infinite number of stars. Could God do that? I guess he could. Anyway, I think maybe we haven't seen anything of what's up there in the sky. And this is why I like day number 4 of the creation week, when God makes the sun, moon, and stars, because it just puts us in our place, that vast number. So anyway, we had that similar sand grains and stars. By the way, to help imagine this number here, just to kind of think about that, 10 billion trillion stars. What if we could take all those stars and divide them up? Okay, one for you, one for me, one for somebody over in France. We could do this for the whole world. How many stars would be your fair share? You'd have to divide this by the world's population, which is 7+ billion. Okay, let's round that off and call it 10 billion. It'll be there soon. If you would divide that number into here, each one of us would have 1 trillion stars. We're all rich. No, they're not ours. You can't spend them. But I mean, you know what a star is, like the sun, putting off more energy in 1 second than mankind has produced since Adam and Eve. Stars are amazing. And they don't belong to us, they belong to God, but that is quite a number. So yeah, as that goes on. Oh, I knew a dog was going to show up here sooner or later. So we're into this little bit of design. And what I want to show you here is that dogs know calculus. What? I said, I barely made it through calculus myself. What do you mean dogs? So this goes back to an article that was written by a fellow, I don't know him, but he's a professor at Hope College up in Holland, Michigan. And one spring day, he took his dog to the beach, this is Lake Michigan, and he was throwing a ball into the water. And the dog would run into the water and get it. You know how the dog gets exercise with this? And he thought, I'm going to study something. So here's what this guy did with his dog. Now, here's the professor, Tim, and he's standing here with his dog, and he didn't toss the ball straight out into the lake, but he threw it way off to the side. See this dotted line? And then he says, go get it. Okay, what's this dog going to do? He could jump in the water and swim all the way over there, straight line, but you go pretty slow in the water, and that would take a while. Or the dog could run all the way down here and then go straight up. But he did this over and over again, and notice that the dog, he called his dog Elvis, the dog would run down a certain distance and then take off at a certain angle into the water to get the ball. And he made measurements of this and found out that what the dog was doing this at a minimum time, because you're slow in the water and but longer on the land. This is the whole idea of calculus, finding maxima and minima. And that's what the dog was doing, getting the ball in the shortest time. Somehow this dog had built in that he learned that and did that. So the guy concluded, yep, my dog knows calculus. I mean, it's pretty cool how he was doing this. And it was kind of a popular article that he came up with. Hey, time is moving along, and I got just a couple more things here, but let me jump out of this whole talk for just a second. This morning I gave I was sharing with at the Shepherd of the Hills Christian School, and they're always a great audience, those kids. And we were doing some hands-on things here, so let me just do that as well, because I brought this along, because this is getting boring, just this talk we have. So this morning we were talking about the days of creation, and we were talking about day number 3, when God made the plants. And I said, you know, kids, I live over in Indiana, and our whole state is full of cornfields. I know you have plenty of those here in Colorado as well. And we've learned something interesting about corn. When it starts to grow, on a sunny day, sunlight hits the green leaves of the corn and goes right down through the stem and goes underground. And if you could dig the dirt out of the way, the roots are lit up. Corn conducts the light right down through the plant, and that's how it gets energy, solar energy. Now, you also are using the nutrients and the water in the ground to grow, but that's part of what they do. And the word for this kind of thing is fiber optics. That's what corn has, the way it conducts light. Some other plants do that as well. So then I told the kids, I said, and I've got some fiber optics along here. This looks like fishing line. And this is interesting stuff. It's kind of like a plastic wire. And, you know, they even send email through this stuff somehow these days. Fiber optics, they're kind of laid it all around the country, really. It's replacing a lot of metal wires. And so we were trying a little experiment, and let's see, can you help me with this? Can you just hold this end? You don't have to say anything, but if you could just hold that, because I've got a little light that I want to shine in this end, and if this is good fiber optics, what I put in this end should come out that end. Okay, so I've got one of these green laser beams here. You know, you got to be careful with these, but here it is. So, we got a knot in there, and that's okay. We'll just let this thing hang here. By the way, folks, if this was like a garden hose, you know, laying in your yard, could you shine a flashlight in one end and get the light to come out the other end? Not going to work. But that's a garden hose. This is fiber optics. So can you just hold that end up where we can see it? Kind of hold it up like the Statue of Liberty. Let me shine the light in this end.
Whoa! Oh my gosh!
This is better than television, isn't it?
That's a cool.
Yeah, good work. You're a good assistant.
Look at the entire line.
Yeah.
Yeah. Yeah, the whole thing kind of lights up. Doesn't take much to impress us, you know? If this was strung clear across Denver, if this is good material, the light would come out that end. It's called total internal reflection, the way this works from the physics world, and it's interesting stuff. And so they're learning how to improve this stuff and make better fiber optics for communications. And what's one thing they're studying? Corn, where you have God's fiber optics made way back there in the creation week. It's yet another example of those designs in nature. We'll talk about biomimicry, I guess, sometimes. Anyway, thanks for your help. We'll clean that up later. Anyway, to finish up our talk here, we got another person, John Napier. So another name from yesteryear, and another mathematician and theologian. He was also a missionary, this guy, along with his early math. Now, these are pioneers that laid down all the math that we still enjoy today. He lived in Scotland, and he challenged his homeland to maintain its biblical heritage. He invented logarithms. Oh, there's a slide rule over there that some of us had back in the early days. In fact, some writings say that he got his idea from the slide rule by studying, it's called a horsetail. Have you seen those kind of weeds in a wet area? And the different sections, sort of logarithmic. We always called them Chinese puzzles, where we pull them apart and put them back together. But he studied that kind of thing to come up with logarithms. And he also came up with the idea of the decimal point, you know, the basics of mathematics, the kind of things that we still use today. So another pioneer mathematician from the past who was a godly man and just great examples for us. Back to another anticipation, and again we're running out here pretty quickly, but here's an interesting one from space. Certain kinds of stars, they kind of wink at us. They blink off and on. They're also called pulsars. They're also called neutron stars. Some of them you can't even see. They're like radio signals, and other ones are visible. And so pulsars. And as they've studied these kind of stars, they realize that they are so regular, the way that they are blinking. Actually, they're spinning. And they are so precise that you can use those for a time standard that competes with atomic clocks, which is about the best thing we have. So here's a natural way to keep track of time down to the nanoseconds, and we need that these days with all of our GPS and everything else. And it's like God put that in the sky for us to finally make use of and find. In fact, remember the purpose for stars back in Genesis 1 for days and seasons and signs, keeping track of time. That's what these pulsars are used for. We keep finding these things. Fiber optics in corn, pulsar stars. I can imagine, that God set these all up in the first place. And the angels are watching us. And then they say, well, they finally figured that one out. How many things we haven't found yet? Most of these ideas are still, hidden in nature, and one by one they're found. So this is what these pulsars really look like. They're rapidly spinning, and they're giving off beams of radiation in certain directions. How would you like it if our sun was like this? Off, on, like a strobe light? It would make you dizzy after a while. Appreciate that. We have a sun that's a very steady light. So anyway, that's a good example that pulsars are a time standard. Well, that was kind of, I did my walkthrough there, 3 cycles. I just put in one extra one here just for fun here. These are my last few slides. This is sort of an extra credit calculation. Remember the calculations? So I just been thinking about this one. I call this a flood footprint. It involves the number of people that we have on this earth since the flood. Now, I don't know how many were around in Noah's day before the flood. There could have been a lot of people. But how about since? So you can come up with a little estimate for this. Can you see yourself in this picture? Here we are going from the flood of Noah's day. I'm going to guess somewhere around 2500 BC, give or take, plus or minus 100 years. We don't know for sure, but it fits right in there. The time of Noah, the time of the flood. And here's today, AD 2017. So how many years roughly has it been since the flood? 2500 BC, 2080, 4,500 years. Got that? Boy, can we fit all of history in since the flood, 4,500 years? We surely can. There's human history. Well, that is, again, about 4,500 years. Now, the thing is, population keeps growing. You just can't stop it. Even in spite of war and AIDS and everything else, the population just grows. In fact, during my lifetime, the Earth's population has doubled. When I was young, we had 3.5 billion. Now we've got 7 billion. Is that true of some of you folks as well? Every 60-some years, it doubles. And it's just kind of relentless the way that goes. And so I'm thinking here, can we use that to come up with an estimate of how many people there would be on the earth today from the time of Noah? Every 150 years. That's quite conservative. So then if you got 4,500 years, and it's doubled every 150 years, we've had about 30 doublings. So now you got to take 6, and then it went to 12, and went to 24, and I know the older people died off, but these are kids having kids, and it keeps growing. Since the flood, with this conservative view of population, how big would this become? You got to do this 30 times. I don't want to do any more math on a Friday night. I'm just going to show you the answer. You have to tweak it a little bit. Actually, it comes out close to 7, maybe 6 point something, but you can make it work close to our present population today. I think this is further evidence that the flood was real, as we already knew, and from that time, we've gotten today's population. How do you like that? Does that bother you, by the way, that the population has doubled during your lifetime? That kind of surprised me when I thought about that. And it'll double again. We'll go from 7 billion to 14 billion to 28 billion, unless the Lord has other plans, and He may well. But it's interesting how population works. So anyway, that was just kind of an extra one. So I'm back to, we did cover the puppy dog and everything else. Again, I don't know what people think of mathematics, and our country seems to be kind of fearful of it. But, we've got the best reason for enjoying creation, including math, because we know who put it all together. And not that we're all math majors, but the more we know about this stuff, just you'll get more out of life. So keep reading all those creation articles, soak up what you can, and it's all good stuff. Hey, that's all I had, but maybe we just have a few minutes for any questions you have or any corrections to what I've said. Anyone have any thoughts before I sit down? Yes, ma'am.
Well, in the beginning, parents had many children. Nowadays, everybody's having less children.
For sure.
For sure. So, you know, it might seem like it's doubling, but not in the United States.
Things are changing.
Yes, they are, for the worse.
Some of these countries are losing people, and they're not sure why. You're right, people are not having children. And now that can be serious because people can lose their culture if they die off. Yeah. So that's an interesting day that we live in. Now, I do know that the U.S., we still immigrate about 1 million people a year, so that kind of helps our population here. But other countries are losing out. Yeah, so the numbers are kind of slippery.
Well, I saw, and I don't know where I have it, but I saw where they had, they wrote out all the different generations from Noah on, and how many children they had. And so they had all these names on this thing, and it was a huge, beautiful tree. And then they said if they would have the same population growth that we had, it was a stump. It was really, I was like, oh my goodness. And they were, and what they were saying is that we should have more children instead of less.
Yeah.
That was their.
So you're right, that doubling time, that certainly can vary over the years. I guess I was just showing that with conservative numbers, you can easily get this population today.
Well, it might double.
It
might take longer than 60 years.
Yeah.
Double.
Yeah.
Definitely is double.
And yes.
When, during the creation week, do you believe God created mathematics? That's something to stump me by.
Well, I would say that they came together on day one when God says, let there be light, and there was light. That includes even those Maxwell equations, because they describe the wave phenomenon of light. So all this complex math is, yes, that's being structured and set up. Well, he's not making it up. It's just
about that, but I don't remember seeing it in writing. He created light. There's light waves, there's all kinds of physics that go into that.
Definitely. And of course, to this day, we don't know what light is. It has a particle nature, it has a wave nature, we just live with it. There's a lot we don't know. And so these equations, they kind of describe our impression of it, but what it really is, it goes beyond us. But yeah, I think the math would be, I expect God already, he's a mathematical God and has that, and maybe was using that in creation, but it had to be there from the start.
I mean, but if there was a creation moment for mathematics, when he says when he created light, that's from my perspective, that's what I think too.
I think so. And even the laws of nature, let's see, the most basic law, conservation of energy. I expect that was established at the end of the creation week, because during that week God is inputting energy, he's making things in this universe from its infinite supply, and then when he's finished creating, then it's kind of in coasting. No more energy coming in, energy's conserved. So yeah, during that week things are happening. He's putting in the math, he's setting up these laws that we've had ever since. And he maintains those laws. Yeah, good thought on math. Yes, ma'am.
I would think of math as the language of science, and in that sense, maybe it's deeper even than the first day of creation. That God is, the incarnate Word is our Lord, Jesus Christ, and so rather than the principles illustrated by equations, but the language itself of the logical language of math maybe is part of the Word.
It is a language, and it's a universal language that everyone can study. It's kind of fascinating. Now, in this postmodern age that we live in, some people are saying that math is just sort of an artificial construct, and that if this whole world was going to evolve again, math would be completely different, that it would be a whole different direction. I reject that. Math is the cornerstone of what this earth has. It's not postmodern at all. It's God's language again. Yes, sir.
I wonder if you've calculated the population growth from an evolutionary perspective, where humans came on the scene maybe a couple 100,000 years ago, and how many people we would have if that viewpoint was true.
It's going to be crowded, isn't it?
I heard that if you crunch the numbers, it's more than the stars in the galaxy.
It certainly would be. So they would have to say in the early stages, it was just not exponential. It wasn't growing like it is today. But from all indications, you can't stop it. It grows like it is today. So yeah, that's a good point. That challenges deep time, for sure. Yes?
When you did the calculation with the sand grains, did that include the sand like in the oceans or just on the seashores?
Well, you know, when I said, let's take 1,000,000 miles of shoreline, I haven't even looked closely at a map, but I think that number, which would be 40 times around the Earth's equator, I think that would include going around all the oceans and around all the islands and certainly around all the Great Lakes. I think that's probably a conservative number, but I don't even know how you find out for sure. And you know, some beaches don't have any sand, but where there is. Yeah, anyways, that'd be my guess at it. I just like to compare that with stars, that number. Yes, sir?
Do you have any other dog or animal stories? Where animals do math.
About herding cats.
Well, the bees,
That's rats.
the bees, they do their dance in order to, to me, that's infinite.
First, certainly.
Yeah, so they do their dance and they
Oh, yes.
tell the other bees where the honey.
They're doing some kind of formula to tell them. There are many more animal stories. We have found out that crows are some of the most intelligent creatures. They can count. What they'll do is you take like a canopy and you have this crow watching, and 9 people will walk under this canopy and disappear, and they'll put some food there, so the crow wants to get the food, but he knows there's people. If 7 of those people walk out, the crow still won't go get the food until the last 2 walk out. The crow is counting people. It's amazing. Animals are limited. We're not animals. We're supposed to manage the animal world, but we continue to be impressed of how God did equip them for survival. So yeah, crows can count. Yes, ma'am.
Well, another example would be bees. And I understand that they communicate to each other by the number of vibrations in their tail. They communicate to other bees
Yes.
where the location of flowers is.
Yeah, that's true. Bees and bees. They also are using polarized sunlight and everything else. And the way they are wiggling these bees, they can tell their partners how far away the flowers are and the direction to them. Yeah, they're communicating on quite a level that we just don't even understand at all. Hey, good stuff. I'm going to quit here. I'll stick around afterward if you have any more sharing. Thanks for listening.